All right, hello everybody. So earlier in the week, we learned about the electric potential due to a single point charge, which is KQ over R. And we also talked about the fact that we can add up the potential due to multiple point charges. And I sense many of you may be shying away because you know what I'm about to do, which is I'm going to think about what happens if I have a continuous charge distribution. How am I going to find the electric potential from that? And I'm going to use the same strategy we used to find the electric field due to a continuous charge distribution. I'm going to chop, multiply, and add. I'm going to chop up my object into little pieces and find dq on each one. I'm going to multiply dq and r and k and anything else I need to figure out the dv due to that part of the charge. And then I'm going to add together all of those little elements of electric potential using an integral to get the net, and my slides are wrong, net electric potential. So that is the strategy that we're going to use. I'm going to go ahead and show you an example here. Earlier, a couple weeks ago, we thought about the semicircle of charge, and we found the electric field due to that semicircle. I'm going to put a total charge Q on here. And I know the radius r of this thing, and I want to know what the electric potential at the center of the semicircle is. Now, you might have a guess from your top hat question, but before I talk about that, I'm going to try to actually figure it out with the full process. So just like we did a couple of weeks ago, I'm going to try to find what is the total charge on this thing. And so I'm going to think about the chopping stage. dq is equal to, I know this is equal to lambda times like ds, the arc length along the circle, and ds is the radius times d theta. So now I've got the dq. Actually, I'm going to go one step farther. I'm going to go ahead and say that I know the charge density is the total charge q divided by the total length of the wire, which is going to be pi times r. So that's actually going to cancel this r out, and then divide this by pi. And I don't know the code for pi, so I'm just going to spell it out. All right, so now I have a expression for dq. I've chopped this wire up into little pieces. So my next step is to multiply. So I want to find dv. And I've got this little blue point charge. I might as well use it, right? So k times dq divided by r, which in our case is just big R, the radius. And then I can plug dq in. So let's see. I'm going to get kq d theta divided by pi r. And that's it. You'll notice that there's no direction for the electric potential, right? Electric field has a direction, but the electric potential doesn't. The only thing that matters is how far away am I from this charge. So I'm actually done already. You can see that this task is a little easier than our electric field one. So the last thing we need to do is say V is going to be equal to the integral of dV, which is going to be the integral, and I better put limits on here. Let's see, just like when we solved this problem a couple weeks ago, we're going to go from minus pi over 2 to pi over 2. So minus pi over 2 to plus pi over 2. Sorry about my drawing here, pi over 2. There we go. And then I'll just put my kq d theta over pi r down here. Now, a lot of those things are constant, right? K, electric constant. Q, total charge on the thing. Pi, obviously a constant. R happens to be a constant here because I'm on a semicircle. If this weren't a semicircle, if it were a straight line or a weird parabola or something, then R wouldn't be constant, and I'd have to figure out what it is to do this integral. But it is constant for us. I can pull it out. So I'm going to get just the integral of d theta, which is theta, from minus pi over 2 to pi over 2, which is going to give me a factor of pi. So actually that pi is going to cancel out, and I'm going to get that V here is equal to KQ over R. That's a little weird, maybe a little expected if you saw what was happening here. All of this charge on the semicircle is the same distance away, and direction doesn't matter. So the potential that I got at this point happens to be the same as we would get from a point charge. So this answer is very not surprising when we really think about the geometry of our situation. In class, we're going to do a harder one where the distance is not always the same and see how we have to handle that. All right. Bye, everyone.